other way. But I'm not sure. I don't know enough about monkeypox. All I know is I don't think we need to worry about it. Because it's been going on since like 2 years ago when they brought it up.
2 years?
It's not new. It's all over the news right now. Oh, you're projecting your picture? Hello, Professor.
Hey,
The accountant office got mad about your signature.
what? Why?
I'll show you.
Oh, it needs to be an e-signature probably.
Professor Sun. Signature there.
Okay, that means they want me to print it out and then sign it and then. Yeah, cause I use the signature tool on Adobe and I type my name out, and puts it in cursive.
Yeah.
Okay, yeah, I will sign it in. I'll probably print it out and then sign it and scan it.
Sounds good.
Yeah.
Like, I was just like, I sent.
Yeah,
it-
they're picky. I mean, it's true. I mean, anyone could have just typed just into Adobe and then sent it. So, yeah, I'll do that.
Also, do you know if you request funding through ICC for you, or is it your own? You have like a professor.
It's a great question. Probably four. Doctor knows I'm really busy. He hasn't been able to talk about it.
Yeah.
I'll ask him.
So.
Yeah, we can request it, it's just a matter of.
I used to do 400.
I sent the message to the
It just helped
director of
work out,
ICC
yeah.
already.
Yeah.
So I'm waiting for their response.
Okay.
Yeah,
Okay.
so I was like,
Where's
hey,
the
you know what, I'm gonna start taking.
I wanted to
into
try to do
the,
the formal
like,
way,
probably like
just
2
like,
weeks and then.
Hey, I do fucking into.
Yeah, I mean,
Is what I wanted to today,
Oh,
but
yeah, the only
I
reason
ate
is
lunch
because
and then.
you have to book it through your own
So-
portal that you.
I see.
So
Yeah,
I click on Thursday, like on
3 classes.
on
back to
Friday
back.
when we talked about it, on Saturday, when I started working on my car, I'm like, wait a minute. He has his own portal?
A little too wide.
I didn't even
my
know
last.
Yeah, and then I was like, wait,
It's like 8.
does he have a different way of funding?
Uh-huh.
But I don't know.
okay, I'll look into it, but yeah, let me know when the treasurer does that.
Sounds good.
Yeah.
Either way, it doesn't look like we're gonna be able to propose next Thursday.
Okay,
Because one of the stipulations was you have to buy the airplane ticket before you propose. You have to have proof of the flight.
oh.
And
And
I-
so you
Wait, what flight?
have to front it yourself.
so one of the trips is, I'm also part of Tau Beta Pi, as you know.
Oh, that's right, that's.
We have our
right.
convention, a national convention where we have professional development through our through like the association. In October for like 5 days, 4 nights. That's a good card. So we're.
Yeah. I mean, I've been part of Tau Beta Pi for 12, 13 years now, but I've not really been. Yeah, it's a good resource.
And the reason we're trying to go on this is like for 5 nights, 4 nights, 5 days, it's 705.
Four nights, 5 nights.
Yeah. It's such a great deal. It's an opportunity for professional development.
I'm hearing a lot of not. What?
So you see our proposal. I got initiated last night.
What?
Tell me.
Is that the engineering track?
Well, honor society, not bad. I just hate it out.
All my friends used to tease me, he's like, are you gonna join, are you gonna go hang with your friend? I was like, it's not a friend, it's an honor society.
Yeah, we're
I
already in the
went-
society.
I went to the initiation at Irvine Society. And everyone's like,
Society.
amazing. I'm like, we're not.
Honor society.
And it's like, you've been talking
We're in
about.
the Society of High.
Tell me about it. I'm like, it's like any other initiation thing. Oh, it's.
That's infinite.
Like you're hating. me. I'm like, "Oh, no."
Safety control.
How many games can you play?
Oh, you wanna play? Either way, yeah, so that's the reason. You're gonna see us request, set it 50.
I'm playing on the computer.
I'll play it with the reload. We're not trying, the other two members are on Rocket and we're trying not to use as much.
Gets 100% from chest alcohol.
Dude, I only trying to request only the amount.
What? They got the money.
We can request over the.
That's
insane.
That's it, they don't take any sponsors or anything. I think they got the extra money. From someone.
Yeah, I did.
Give it back every day.
The request for smart. We have.
Bro, oh, no,
I think it's a new thing that they added. We should get sponsored, like, we can't buy them.
Oh,
That's why we're requesting the money.
Yeah, imagine like seeing someone else's crowdfunding, it says like goal of 10,000 and they reached it.
Oh, yeah, no problem.
Whenever you have time, just.
Yeah,
still
yeah,
have
I'll,
that.
yeah, I'll do it when I get back, Michael.
Thanks.
Yeah.
Also, nice.
So lecture again.
Lecture again, yeah.
They barely got Katsuya working over the weekend.
Yeah, I know, there's,
sad.
our license server got borked, so we're working on it right now, so.
We should change it to
Hopefully it
MS.
goes
What happened?
Change it to
It's,
application.
I heard they
Well-
they canceled all the subscriptions.
We have it,
Well, answer.
yeah. We have the subscription, it's just accessing the licenses, yeah,
Abacus is the number.
there's some issues with that. It's an IT thing, so I really second.
No.
I've never used that. Not really, it's just, we're just understaffed. So someone that was supposed to do it is, not working.
You don't have to.
No.
And,
no.
You guys said,
We should do
We
it.
used to take it
level
out.
5.
oh.
yeah. It's like, wait, it doesn't, it just work.
Have you used Abacus?
I went sitting
Yes.
look at that.
No, same as that SolidWorks.
The only thing that's special about the 6-2-1 is that you can make your own deposits.
Oh, no, it's Sam,
In
Alex,
in Abacus, it's the most updated one. I think research is being made in all of the Abacus.
It's always good, you know.
They're all the same thing.
Yeah, well, yeah.
It's
Let's
just
see, what's my rating?
one and
My rating is a.
0.
Alright.
Oh, it's not, you know, the times I spend in my business classes, this is what it is the entire, it's still done in chess.
Lost.
Yeah.
I'm just,
Good.
we're trying to see if I can organize one before the kids are in midterm season. Or after midterms, just to see if I can organize something. Might be taking my isolation and bullets.
Yeah, that's why I wrote for this intern. I
Oh.
told him that I want my team near should be on part. And then just all the way, took my cover and then, like, proposed it.
We have
What's your? Excited about you. That's. Which part?
Yeah, near like Rowan Heights. Or if you have, like really possibilities and just, it's like.
The last like I have. I was hoping to finish that one. We didn't finish it.
Is that a bond?
It's He had surgery a year ago.
I lose my luck.
Alright, it's 5:30, let's go and get started. Alright, good afternoon, everyone. How's everyone doing today? Good. Good. It's another ANSYS list day today, unfortunately. So just a little bit of information, you guys. So our license server is having some issues right now, so we are working through it. IT is on the case. It's a very high priority item for them. It's just gonna take some time just to work. So I unfortunately don't have an estimate about when it's gonna be fixed. I'm hoping it's gonna be ready for us by Thursday. But if not, then we'll just kind of adjust from. Don't worry, I have plenty of stuff I can lecture on, so you guys won't be bored, because I have so much fun theory of finite elements that I can share with you before we do the answers. But of course, this does mean that the due date for activity 1 is to be pushed back. I think originally I had to do for this Friday, but obviously that's not going to happen if we don't have answers. So I am going to push it back. It's just to be determined. But so whatever day that we can get to do ANSYS, the due date will be basically a week after that. Okay. So if we're able to do ANSYS on Thursday, then the due date for activity 1 will be next Friday. Okay. And generally the pace that I have for this class is that every other week we do an ANSYS activity. So we're still on track just fine. It's just things just have to shift around. Okay, so the plan for today is we're going to do a little bit of review today. So like I mentioned on last Thursday, that the majority of this class, even though finite elements is kind of a general methodology, you can use it to simulate almost anything that's governed by a differential equation. Just for the purposes of this class, just to kind of keep things kind of kind of organized. We're going to focus mostly on structural simulations. I think it's generally the most relevant, I think, for most of you guys too for your senior design projects. And so to kind of understand some of the features and some of the plots and some of the things that you're going to see in ANSYS, I think it's necessary to just do a very quick review of some important concepts from strength of materials. I don't think it's going to take all of today. And so if we finish that a bit early, we'll move on to a little bit of meshing. Okay. All right. Update on the wait list. And so I think just because there's another elective offered this time 490. I think quite a few people have kind of moved to that. But if you're further down on the wait list, I think I'll be able to accept people 1 through 5 on the wait list. I think that's fairly safe. But if you're position 6 and beyond on the wait list, I would look into other options. So if you're looking for something at this exact time slot, EGME 490 is an option. And so that is a design thinking class. It's a new class, and so I think it's kind of exciting in that sense. And it's something that's I think is actually more relevant to senior design. Definitely check that out. If you have kind of extenuating circumstances where if you're kind of low down the wait list, you can come talk to me. I can try to make the argument, but because we have that other technical elective offered at this time, it's going to be a little bit of a hard sell to get you into this class. So if you're still on that wait list, if your wait list 1 through 5, I think you should be contacted by the department, hopefully fairly soon, with the permit and instructions. But if you're further down, just I would look into other options at this point. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the subject for today is a strength of materials review. Okay. So a lot of the of what we're going to do in this class with ANSYS is going to be structural simulation. So we're going to do a lot of static structural, we'll do a little bit of transients as well, a little bit of vibrations. And so having a good background in solid mechanics, strength of materials is really helpful for kind of interpreting a lot of what we're going to do in ANSYS. And so that not only goes for the boundary conditions, but that especially goes for interpreting the results as well. Okay. All right, so let's start with kind of some very basic concepts. So let's talk about the concept of stress. Okay, so when we talk about stress within the context of structural mechanics, solid mechanics, we're talking about internal forces, basically. So stress is actually a very complicated thing. But if you were to kind of sum it up within a single sentence, I would say that it's basically the internal forces that develop within structures that that basically keep equilibrium with its external environment or any external forces. And so, of course, when talking about equilibrium, we're talking about kind of a static case here. Because if you have a structure, and so I'm just going to use a simple beam just as an example. And so if we were to apply an external force on this beam, and so let's say, I'm still on rainbow. And so if we were to apply a force, an external force P, okay, in order for this to maintain equilibrium, in order for the entire structure to maintain equilibrium, there has to be an equal and opposite force being applied on the other side. So that force could also be, it could also be an external force, and so you could have just two guys kind of pulling on it like a tug of war, okay? Most oftentimes, any kind of stabilizing force is going to be a reaction force. Those of you who just came from optimization, there's going to be a little bit of terminology whiplash here, and so I'm using the term constraint here, but of course constraint means something different here than compared to optimization. So constraint in this case is an actual physical constraint. Okay? So usually, if we have this beam here, usually it's attached to something, it's welded to something, and so that reaction force is coming from that. Okay. So that's equilibrium. So we kind of understand that all the way back from statics class. Is that the sum of forces on an object in in static equilibrium has to be equal to 0. Okay, so in order for this beam to be statically equilibrium, all the horizontal forces have to cancel. But this concept also applies for internally as well, right? Because at every single point in this beam right here, every single point in this beam is also in static equilibrium. So that means internally as well. So that means if we were to take this beam and if we were to slice it open, and so if we were to kind of take this beam and let's cut a cross section like this, if we were to cut a cross section like that. And so on this cross section here, we still have that external force P, right? But this segment here, just by nature of being part of the original structure, this segment also has to be in static equilibrium. And so, just by the rules of Newton's laws, there has to be an equal and opposite force on this kind of subsection here that keeps it in static equilibrium. And so the way that equal and opposite force kind of manifests in this situation is through an internal stress. And so the way that we kind of visualize that is through a distributed force on the cut section. So this right here is a distributed force on the internal cross section. Whose main purpose is to maintain static equilibrium. And of course, what we call that force there, what we call the distributed force, that is stress. So stress is a concept that we're going to be dealing with a lot in this class, right? So the idea is that if you have kind of a static structure, you apply some kind of external loading, external forces, there's going to be some internal stresses that develop within the structure to keep each segment in equilibrium. All right, so what are the units for stress? Right. So, just like the definition implies there, stress is a force distributed over an area. Stress equal to force area. If we plug in the SI units for both of those quantities, and so the SI unit for force is newtons. The SI units for area is meter square. That's the SI unit for stress, okay, Newton per meter square. This shows up a lot in physics, and so it's named after the scientists, just like most things are in science. Okay, and so the SI unit for stress is the Pascal. Okay. So Pascal, I would say, or this idea of a force distributed over an area is, I think, one of the most widely used units in structural mechanics. It's not only used for stress, it's used to define pressure. Young's modulus has the same definition, so this unit is used a lot. And it can be kind of confusing as to kind of, keep track of what's what, okay? And so what I want to talk about right now is just kind of the comparison of stress and pressure, because those two kind of get compared to one. So just like stress, the units for pressure is Newton per meter squared, force over area. So how are they different? Okay. Technically, you could say that they're kind of the same because they represent kind of the same physical phenomenon, force distributed over area. But how we talk about them, how we actually use them is kind of different, kind of mostly in terms of context. So stress. Stress is usually used to describe something that develops internally within a material in response to some kind of external load. Okay. So stress is almost always talked about as kind of response. Okay. And so you apply some kind of external load onto a structure, the stress is going to develop in response to that to maintain equilibrium within the structure. Pressure, on the other hand, is usually the aggressor, I would say. It's usually used to describe some kind of external force that's being applied to something. So that's usually the distinction that you see. Stress is an internal thing that develops in response to something. Pressure is an external force that we usually apply to something. Okay, and you'll see this kind of same kind of convention used within ANSYS itself. Right? And so if you wanted to apply kind of an external kind of distributed loading boundary condition, you would apply that as a pressure, right? So pressure is very much an external boundary condition that you apply to a structure, whereas stress is usually the result of the simulation, something that you can view afterwards, something that develops internally. Okay. And of course, this distinction right here, this definition is kind of a purely kind of a solid mechanics type distinction. The concepts of stress and pressure are also present in fluid mechanics, and they take kind of a slightly different definition there. But for our purposes, this distinction here is what we're going to use, and is basically what's consistent within ANSYS. All right. Any questions on this? Okay, cool. All right, so kind of going back up to this figure here, right? If this stress here has to be kind of oppose this force, then we can actually come up with an equation for this. And so if we call the stress sigma, right? That's usually the symbol that we give for stress, right? If this entire kind of subsection here has to be in static equilibrium, we can say that sigma multiplied by the cross-sectional area this has to be equal to the applied force P. Okay. And so through this equation here, we can actually come up with a very rudimentary definition for the stress. The stress is literally equal to the applied force divided by the cross section. And that kind of lines up with our definition that's down below. Okay, so stress is something that develops, in response to an external force. So its value has to also depend on that external force. Okay. So that's just kind of the very basics of stress. What stress is, how, why it develops, and kind of a basic definition. Of course, stress is a lot more complicated of a phenomenon than this. Okay. Unlike force, stress is actually a tensor quantity, and so we also have kind of directions and components of force. So stress usually has multiple components and directions. Okay? And so there are kind of multiple ways that you kind of look at this as well. So first thing we're going to describe it are kind of two, I would say, kind of broad classes of stresses. And so the first class are what we call normal stresses. And just like the name implies, these are stresses that act perpendicular to the cross section. So the stress that I kind of showed up there with the kind of the beam and tension, that was a normal stress, right? Because the cross section was vertical, but our stress components were horizontal, so that was acting normal to that surface. And then the other kind of broad class of stresses that we have are shear stresses. And so kind of opposite to normal stresses, shear stresses will act parallel to the cross section. a visual kind of illustration of this. Normal stresses will act perpendicular to this, and so this. Where shear stresses are going to act parallel to this. Roll later colors. All right. And so beyond these two types, we can further break down stress into its different components. Remember, stress is actually a tensor quantity, so that means it's characterized by a matrix. It's not a scalar, it's not a vector, it's a matrix. So the way I usually denote matrices, it's not going to be, you're not going to see it that much in this class, but the way I describe matrices, I put 200 lines underneath. Okay. And so the stress tensor, at least in its kind of standard kind of Cauchy form, speaking about the following. So it's a 3x3 tensor when you're talking in three-dimensional space. We have the main diagonal components, so we have sigma xx, sigma yy, sigma zz. So the diagonal components of the Cauchy stress tensor, these are the normal stresses. Of course, they are labeled by their direction. So sigma xx is the normal stress in the x direction, sigma yy is the normal stress in the y direction, and sigma zz is the normal stress in the z direction. Then we have the shear stresses. So those are characterized usually by the symbol tau. Okay. So we have tau xy, tau xz, and tau yz. So all the tau values, these represent shear stresses. And the two components, represent the face that they act on, right? Because in order to be parallel to a particular surface, you have to define where that surface is pointing. And then the second component there tells you the direction of the force itself. Okay, because in any kind of two-dimensional plane, so you can look at a piece of paper for instance, there are two kind of perpendicular directions that are parallel to that plane. So you can either go this direction that's parallel to the plane, or this direction that's parallel to the plane. Right? And so when you're talking parallel to the plane, you have to specify which direction parallel that you have to go. Okay? So that's why there's kind of two components given for the shear stresses. All right. And so in total, we have we have 6 components there, so 3 normal stresses, 3 shear stresses. But you're probably wondering, this is a 3x3 matrix, and so there should also be 3 components below the diagonal as well. And you would be correct. We have tau yz here, tau zx here. Sorry, that's tau ys. A little bit of break for it there. And then tau z1. So the reason I didn't list those at first is that these components are, or this matrix is symmetric, right? So tau xy is the same as tau yx, tau xz is the same as tau zx, and tau zy is the same as tau yz. Okay. So even though the stress tensor is a 3x3 matrix with 9 components, there's only 6 independent components. Okay, because the shear stresses are kind of mirrored; they're identical across the diagonal. So the reason we're going over this is that in ANSYS, you'll be able to view, right? So if you run a simulation on a part, you'll be able to view things like the normal stresses and the shear stresses, and you can break them down into the different components as well. Okay, and so it's kind of really useful to kind of go over this definition, just because that's kind of how ANSYS kind of display the information to you. Okay. And so you'll see this actually really come into play for probably ANSYS activity 3. And so in ANSYS activity 3, we're going to do a simulation of a signpost, right? As you can see, you're going to see in that activity that there's going to be a very prominent normal force or normal stress in one particular direction compared to the others. Actually, you'll probably see this in activity 2 as well. And so it's really useful to know kind of the different components and kind of what they. All right, any questions on this? Okay. All right, hopefully this is all kind of good review. All right, so that's stress. Let's go over the concept of strain. All right, so if stress is a kind of the representation of the internal forces within a structure, strain is a representation of the internal deformations within a structure as it's being deformed from an external force. Okay. Because not only, for an elastic material, right? If you expose it to an external force, yes, there's going to be internal forces that develop; those are stresses. But there's also going to be deformations that occur as well, right? If you apply force, if I were to apply, a force to this pencil, right? I'm not going to do this because this cost me $60 and the school's not going to pay me back for it. But I can, bend it like this, and it's gonna deform in response to that force, right? And that's usually what we describe as strains. So how we actually quantify strains is a little bit different than stresses. And so if you look at the units for strain, it's actually dimensions. So there's no dimensions associated with strain. No dimensions, no units is kind of the same thing. And the reason for this is that the way that we kind of traditionally describe strain is it's described as a relative deformation. So it's a change in length, kind of in kind of the most traditional 1D sense. It's a change in length divided by the original length. So I think when most people learn about strain for the first time, it's in a 1D case. You have some kind of spring or you have some kind of beam that you're stretching, okay? And strain is just the change in length over the original. Of course, in 2 dimensions and 3 dimensions, this definition is kind of expanded. 2D and 3D deformations you can't really describe as just a linear change in length, but it's the same kind of idea. So it's a change in it's the relative change over the original dimensions or the original size. Okay. Let me kind of draw the original kind of definition for you. You have a beam, you're pulling on it. It's going to lengthen like that. Okay. So if this right here is delta L, and the original length of the beam is L. Okay. Then the strain, usually we give the symbol epsilon there. Okay. The strain is going to be the change in length delta L divided by the original L. All right. Any questions on this so far? Okay. And so just like stresses, there's a concept of normal strains and shear strains as well. And so just like stress and strain is also a tensor quantity, and so it is represented by a matrix. I'm not going to draw the matrix for you again. It has literally the exact same structure as the stresses. But that is kind of important to know, right? And in fact, it's no coincidence that stress and strain have the same structure, because a lot of times they are very closely related. The exact relationship or the exact dependence of stress and strain depend on the material model that you're using. Okay. In the most simple sense, these two are linearly related. So that's kind of what we described on last Thursday. So for a linearly elastic material, stress and strain are related linearly. And so stress for linear elastic material, that stress is equal to the Young's modulus multiplied by the strain. So we saw this equation last week. Okay? Where this E here, of course, this is the Young's modulus or the elastic modulus. And because they're so closely related, you'll see in all of our activities. Usually I'll just have you plot the stress, and so I'll say, give me the stress plot. Just because the strain plot looks literally identical, it's just the numbers will change. So for a linearly elastic material, there's really no point in plotting both the stress and the strain, because they look basically identical. But if you have a more complex material model, like let's say a hyperelastic material model, or you have plastic deformation, it could be useful to plot stress and strain separately. But if you're talking a purely linearly elastic material, these two are practically the same. And so the only difference that you'll see is that they differ by a factor of the elastic matrix. So, for this class, for the vast majority of cases, we're going to be working with linearly elastic materials. And so for the activities and stuff like that, I'll only ask you to plot the stress, just because the strain plot looks identical. Any questions on this? Okay, so that's stress and strain. So let's go over the concept of a principal stress and a principal strain. Okay. So just to kind of reiterate kind of what I mentioned earlier is that the state of stress in a material is often very complex. So in most practical cases, or maybe I should be more precise. Instead of saying complex, it's complicated, right? Because complex can often imply imaginary numbers, which I'm not saying that's the case at all. So it's just complicated. And by complicated, I mean that you have three components of normal stress, you have three components of shear stress, you have to take their direction into account. It can be a lot to to think about. Okay. Oftentimes, when we think about stress, we want to kind of simplify our interpretation as much as possible. Because oftentimes, when you're doing the simulations, a lot of times you're not really interested in the intricacies and kind of all the different components of stress that result. Oftentimes you want to kind of just do a very simple kind of stress analysis, and so you want to simplify your pipe as much as possible. And so we usually do the simplification kind of in one of two ways. So computing the principal stresses is kind of the first way. But the way that we'll use kind of most often is called the equivalent stresses, which I'll go over after this. Okay, so let's go over principal stresses first. And so the idea with the principal stress is that instead of dealing with 6 separate components of stress, the idea behind principal stress is that, what if we perform a change of coordinates, right? So maybe we rotate our reference frame such that we kind of, eliminate some components of stress. And so the terminology that we typically use for this is that we zero out those okay? Let me kind of give you an example, right? So, of course, stress is a tensor, right? And so it has multiple components in multiple directions, but I think this idea of kind of zeroing out a component is most easily kind of visualized in 2D with the ball. So let's say that we have a vector. Right, so here's our vector v. Right, traditionally, we describe this vector using its x and y components, right? And so the x and y components are basically, if we were to draw kind of a Cartesian coordinate system here, we have our x-axis that goes horizontally that way, and the y-axis that goes vertically upwards like that. And so, if we were to describe this using the Cartesian coordinates, we have its x component, which is v sub x. Okay. And we have its y component, v sub y. Okay. And so we can describe the vector as vx v. Right. So two components to describe a two-dimensional vector in two-dimensional space. Okay. Pretty straightforward. But what if we wanted to zero out one of these components? What if we only wanted to describe this vector with only one component? Okay. One way that we can do that is we can rotate our reference frame. So instead of looking at it, with a traditional horizontal x and vertical y, what if we rotate the reference frame up so that one of the axes aligns with our vector? So let me redraw our vector v here. So what if we rotate our reference frame so that it's parallel with this vector v? Okay? And so we kind of, this is our original x here. I'm going to draw with the kind of a dotted line. What if we rotate it upwards like this by an angle theta? So that our x-axis, I'll call that x prime, is now parallel to the v vector. And then y prime is now perpendicular to that as well. Okay. And so now our vector v, we can describe its components as vx prime, right? Which is the component of the vector in that x prime direction. And since the y prime direction is perpendicular to the vector, it has no component there. And so its component in the y prime direction is 0. And so basically by performing this rotation of our reference frame, we have zeroed out one of the components, and we're now left with just one component to describe it. Okay. And so for principal, principal stresses basically takes this concept of rotation and applies it to tensors and applies it to 3D, which is exponentially more difficult to draw. So I drew it in 2 dimensions with a vector here, but it's the same kind of idea. Okay. So for principal stresses, for a typical kind of part right here, and I'll kind of draw in 2 dimensions so you can see. Okay. So typically for a part like this, we have normal stresses in all directions, and we have shear stresses in all directions as well. So here we have our full kind of stress assortment here, normal stresses and shear stresses. But under the principal stresses, what we can do is we can rotate this. And so instead of viewing the stress components in terms of this kind of horizontal and vertical square, if we kind of rotate it so that it's kind of more like this. Okay. The idea behind principal stress is that there exists a rotation, or there exists a change in reference frame such that we can kind of zero out all of the shear components. And so under this configuration here, we kind of redraw our normal stresses to align with the rotation. But we performed our rotation so that our shear stresses are zeroed out. Right, and so instead of having six, instead of having six kind of independent components of stress, we now have three independent principal stresses. So we cut down our stress components from six down to three. So you can see that's a big kind of reduction in our, in our interpretation. And so of course, there's three principal stresses. So that kind of begs the question of what do we call them, right? We call them the maximum principal stress. There's the minimum principal stress. And so what's in the middle of maximum, minimum, and minimum? We have the middle child. So we have the middle principal stress. Okay. Usually, we're mostly interested in the maximum principal stress. Sometimes the minimum, sometimes the middle, but maximum principal stress is usually the one we're most interested in, because that represents kind of the highest, we call it the highest stress component, the highest normal stress component. So what you'll see in the activity that we'll hopefully do on Thursday, we'll compute the maximum principal stress. All right, any questions on this? Okay, cool. All right, so that's one way that we can kind of simplify our interpretation of the stress. The other way that we can do this is by computing what's called the equivalent stress, or otherwise called the von Mises stress. So this is the one that you'll probably see most commonly in this class. So, through the principal stresses, we were able to kind of reduce our stress components from 6 down to 3. But what's simpler than 3 is 1, right? And so the equivalent stress basically takes our 6 stress components and kind of boils it down to 1 kind of stress magnitude. And that's kind of the best way to kind of interpret the equivalent stress, is that you can kind of think of it as like a magnitude of the stress. So just like you can compute the magnitude of a vector, the magnitude of the vector is essentially just the length of the vector itself. There are ways to compute kind of like a norm of a tensor. They don't really have as physical of a definition as kind of the magnitude of a vector. So this is kind of as close as we can get. Okay. So the formula for this, and I always forget that I don't have it written down. So actually, let me look it up real quick. So the formula for it is sigma Vm every time I look this up, it asks me if I want to do any shopping at Vaughn's, which I don't. Okay. So the formula for this is given by the following, so it's a bit complicated, so it's square root. Just like every good magnitude formula, there is a square root involved. And we have 1/2 multiplied by the quantity sigma xx minus sigma yy squared plus sigma yy minus sigma zz squared plus sigma zz minus sigma xx squared, right? So those are all the normal components. And then the shear components look like the following. So plus, all the shear components are kind of bunched into one. So we have 6 times tau xy squared plus tau yz squared plus tau xz. So that is the formula. This formula here, I'm not going to ask you to compute anything with this formula. It's kind of just is what it is. But just know that when you view equivalent stress or von Mises stress within ANSYS, this is the formula that it's taking to compute. Okay? So it's not just a magical stress that's unrelated to the other stresses. It is related. It just takes all 6 components and then kind of computes one formula from here. Right. And what we're going to use this formula most, or what we're going to use the equivalent stress to the most, is we're going to do this to do a lot of failure testing in ANSYS. And so this formula has kind of been specially kind of derived so that you can compare it to the yield strength of the material. And so to see if a structure will fail, oftentimes we'll use ANSYS to compute the equivalent stress, okay? And we're going to see if the maximum equivalent stress, or the location where the maximum equivalent stress occurs in the structure, we want to see if that exceeds the yield strength. And so what we basically say is that if the equivalent stress, or the von Mises stress, exceeds the yield strength of the material, so this on the right here is the yield strength. So the yield strength is a property of the material itself. So aluminum has one, steel has one, right? It's basically the maximum. This is basically the maximum internal strength or internal stress that the material can, withstand before it starts to fail. So that will almost always be given to you, but it's also something that you can look up. It's a very common property. Okay, and so from our simulations, if our von Mises stress exceeds this yield strength, then our then your structure will fail. Okay, so remember this von Mises stress. This is something that's computed from the simulation. And if that exceeds the yield strength, then you should redesign your rear wall. Okay. All right. And in addition to this, a lot of times when you're designing structures, you want to work within a certain factor of safety. You usually don't want to design something so that it gets right up to the point of failure. That's usually, that's usually asking for trouble. And so usually, the actual formula that we use is something that looks like this. So we have 1 over gamma, where this gamma here is the factor of safety. Okay. 1 over gamma multiplied, oh, excuse me, I did a reverse, so it should be multiplied by gamma, sorry. Okay. So gamma the numerator, multiplied by the bond Mises stress. If that's greater than or equal to the yield strength, then your structure is going to fail. Okay. So the factor of safety kind of adds kind of a buffer for. So I don't think we'll do anything with factor of safety for the first activity. First activity, we're just kind of getting used to ANSYS. But second activity, we're going to start to get, work factor of safety in there as well. Okay. And ANSYS can compute factor of safety for you. That is kind of one of the newer things that it can do in the newer versions. But I'll show you kind of how to factor in factor of safety, kind of a bit more manual. All right. Any questions on this? Okay, so the last thing I want to talk about today, before I let you guys go, is this concept of the Poisson's ratio. So the Poisson's ratio is often given by the symbol nu, which looks like kind of a squiggly V. So the Poisson's ratio is one of two kind of essential parameters that you need to specify for a linear elastic material. So there are two material parameters that you need to specify for a linearly elastic material. So one is the Young's modulus E, and the other is the Poisson's ratio. Okay. Interestingly, you technically don't need the density. So density is actually not a not an essential property. Although if you want to factor in the weight of your object, then you need to do density. But if you're talking strictly just on linear elasticity, the only two materials you need are just the Young's modulus and the Poisson's ratio. Okay. I believe we talked about Young's modulus last time. Young's modulus, remember, represents kind of the strength of the material or how well it can resist deformation. Poisson's ratio is a strictly kind of multi-dimensional parameter. And so what the Poisson's ratio basically measures is that it measures how much a material will deform in directions perpendicular to the load. So the exact kind of effect of the Poisson's ratio, it is actually quite complex. But just to kind of give you an example, right? This kind of results mostly just from the phenomena of conservation of mass, right? And so conservation of mass basically states that whenever you have a certain structure, you're working with a fixed volume or fixed amount of material. And so if you're going to stretch in one direction, that means you're going to you have to thin out in another direction just to maintain the mass, right? And so let's go back to our beam from earlier. And so we have kind of a beam here or any kind of rectangular piece of material. We can kind of pull on it. So let's say we pull on it with equal and opposite forces P in each direction. Okay. The natural thing that we expect is that this material will deform, and so it'll start to stretch out. So it's going to elongate, right? But because of conservation of mass, you can't have just simple elongation just by itself, right? So in order for it to elongate, it also kind of has to narrow as well. And so the ending geometry actually looks kind of something more like this. It's this. So the ending geometry, I'm going to exaggerate a little bit. Usually it's not this much. So the ending geometry looks something like that, where it's elongated in response to the external forces, but you can see that the entire material has also kind of gotten skinnier as well, right? And so of course, different materials have different Poisson's ratios. Somehow in my mind, I always have this kind of, whenever I write ratio, I always want to put an N, like ration. I think I'm just hungry, like I usually am this time. Okay, because of course, different materials are going to resist this more than others, right? And so if you pull on a material, right, it may want to elongate in a certain direction, but it may not want to, become skinnier, right? And so that Poisson's ratio kind of expresses how easily it can do that, right? So for most elastic materials, oh, by the way, Poisson's ratio is dimensionless, just like the strain. So there's no units associated with it. So for most elastic materials, the Poisson's ratio will be somewhere between 0.25 and 0.35. The most extreme case is that if you have an incompressible material, and so for a completely incompressible material, Poisson's ratio is 0.5. And 0.5 is the maximum value that you can have for Poisson's ratio. Poisson's ratio exists between either 0.0 or 0.5, somewhere within those bounds. Okay, and it's just like the strain. It's a ratio type quantity. So it's a ratio of how much perpendicular deformation that you get to parallel deformation. All right. Any questions on this? Okay, I think we'll call it here. There's about 10 minutes left, but I think that's a bit too short of a time to start meshing, so we'll call it here. Hopefully on Thursday we'll be able to do answers. I'll keep you guys updated on the device and server situation, but we may have to push the first activity to next Tuesday. I don't know if not. But IT is working kind of around the clock on this. I think hopefully they're working on it. But thank you guys for coming today. I hope you guys have a good rest of the day, good afternoon. And I'll see you guys on Thursday.
Oh, so rude. All right.
Professor, do you mind scrolling up to equivalent stress?
Oh, say again, sorry.
Do you mind scrolling up to your notes where you say equivalent stress?
Yes.
Oh, yeah, right there. Yeah, thank you.
No, two would be insane for like that's way better. She also paid for it, not gas here. My section.
I didn't see it go. Sounds like it was- That's good. You go.
You brought that up.
Those like, you're gonna like.
Pinball up there, it's like ball, pinball, basically, pinball.
But,
Oh,
one of them, I got lost. It took me like 3 hours.
Oh, it's happening, man.
Yeah. But it's pretty fun,
Yeah, that good, Rich.
I think that I saw, what is it called? Snake? Yeah. But it's pretty nice, it's really nice, it's like shaded and some very good. From here, maybe.
What do you?
It's that one and also, if you have anyone near like the, grounds, like Berkeley. And Annie was really nice too.
I live here,
Yeah, they put some data.
but I've got a trail here. And right there, you can swim in the river.
I've only gone to like up to the waterfall, but never really gone into it. I fell in the river a couple of times, but not. waterfall.
I just had
The show bit? Right here at the show.
Yes, sir.
The gift over like this, we've seen.